Okay, so we're going to be looking now at what sounds like what we just looked at, um, arithmetic series, but it's not quite what we were just looking at. So previously we talked about arithmetic sequences, um, which are lists of numbers, effectively. And now we're going to look at arithmetic series, which are also a list of numbers, but they effectively derive from sequences, and we'll see how in a moment. But I just want to make it clear that we're talking about two key words, one of them being sequences and one of them being series, and they are not interchangeable. They mean two very specific things. Outside of mathematics, you sometimes might hear people using them interchangeably. They might say, oh, look, I've got a series of numbers here, I've got a sequence of numbers here. But within mathematics, we have to be careful. Those terms are precisely defined and they don't mean the same thing as each other. Okay, so we're going to be talking about series today. To just start off, you may have heard this story before because it's one of those famous stories, which typically, as is always the case, seems to turn out to not quite be true, but people tell it anyway because it's a nice story. I don't know if this story is true or not, but it doesn't particularly matter. The person in the story is real though. Gauss. So he was, or I suppose, well, yeah, throughout his life he was German, but he was born, I think, in the 1700s. It's a few hundred years ago now. And when he was in elementary school, as the story goes, a teacher gave him the task to keep him busy, as teachers are wont to do. He was a bit too smart, always asking for more work, and so teachers just said, fine, add up the numbers from 1 to 100, see if you can do that. That should keep you busy for the lesson. And the story goes that within some amount of short time, let's say in a minute, he just gave the answer. He added up all the numbers from 1 to 100 in less than a minute, without having put pen to paper, entirely in his head. And this was apparently quite impressive, which makes sense. And this was supposed to be a sign that this Gauss would go on to do great things. So whether the story is true or not doesn't matter, as I said, but it's an interesting idea. If I asked you to add up the numbers from 1 to 100, could you do it? And more importantly, can you do it without just using a formula? So you probably already know a formula, for instance, for triangle numbers, which might give you the answer. So spoiler if I just told you one way of doing it there. But I don't want you to use any formulas or any sort of methods which have already been proven for you. Can you imagine you wanted to explain this to someone who knows nothing about formulas? They just, average person on the street who understands basic mathematics. They know how to add, divide, and subtract and multiply. Can you convince them of your answer? See how you do. How do I add up those numbers? Can you think about that for a moment? Okay, so I'm assuming you paused because that wasn't quite enough time, unless you were Gauss. So here is how we're going to do this. There's actually multiple ways of visualizing it, but here is a very cute, very slick way of doing it. You're adding up the numbers from 1 to 100, but what you're going to do is you're just going to add them up in the wrong order. So I'm going to do 1 plus 100, then I'm going to add 2, then I'll add 99, then I'll add 3, and then I'll add 98, and so on. And what's the last sort of pairing I'm going to have? It's going to end up, I want to be careful here. Well, in total I have 100 numbers, right? If I consider these as pairs, then I'm going to end up with 50 pairs. So if I call that one the first, and then the second, and then the third pair, that should make it clear. We end up with 50, and then plus 51. Okay. And what's the point of doing it that way? It's because in each of these pairings, we end up with the same number as total. So 101, 101, 101, and 101. Okay. How many pairs are there? there's 50 pairs. Each totaling 101. Oops. So to find the full total, I'll just do 50 times 101, which you can also, I think, legitimately do in your head, right? It's just going to be 5,000 plus 50. So you get 50/50. And that's it, that's the answer. Okay, so I really like this because you don't actually need to understand the formulas for any of this. As I said, you could explain this to anyone, even if they haven't particularly gotten that far in their mathematical understanding. And that's it. That's the sort of the story of Gauss, and how he added up the 100 numbers. You can see him actually here, just for illustration. A bit of backstory. This is the German Deutsche Mark when it existed before euros were invented, and when European countries all had their own currencies. So they put him on the 10 Deutsche Mark note, precisely because he was such a a famous mathematician and was so fundamental in a lot of the things he invented. In fact, if you do zoom in, I don't think you can see it at this resolution on YouTube or wherever you're viewing this, but there's actually a normal distribution graph here on the banknote. And even if somehow you ever get hold of a 10 Deutsche Mark, which might be a bit difficult, if you maybe track down some older Germans and ask them for their stash of old currency, you can look at it and it will actually have the formula for the normal distribution on there. So that's quite nice. But anyway, they don't have that on the euros anymore. Cool, so this is the main concept. Anecdotes aside, this is the concept: pairing numbers together and using that to find a shortcut for adding things up. And that's what we're going to be looking at today. Okay, so first let's define an arithmetic series before we start using this pairing concept. An arithmetic series, effectively, it comes from having initially defined an arithmetic sequence. It wouldn't really make sense to talk about series before we talk about sequences. I think the easiest way first is to just give you an example. So let's say, well, let's talk about the one we just looked at, which is numbers 1 to 100, right? Or let's just say 1, 2, 3, 4, 5, and so on. Okay, this is a sequence, right? It has an A of 1, it has a D of 1. In this case, it's an arithmetic sequence. Okay. Now, a series is the idea of, well, I've got a sequence and now I want to add up the values in that sequence, right? So if I add up the first value, well, what does that mean, adding up the first value? It means I don't do anything really. I just end up with 1. If I add up the first two values, I do 1 plus 2, I get 3. If I add up the first three values, 1 plus 2 plus 3, I get 6. Add up the first 4, 1 plus 2 plus 3 plus 4, I get 10, and so on, I get 15. So this is an arithmetic series. Okay. So an arithmetic series, it's still a sequence, right? It's a sequence of numbers, but it's not an arithmetic sequence, right? Because the difference between these numbers now, 1 to 3, 3 to 6, 6 to 10, they're changing. So it's not an arithmetic sequence. So I'll just repeat a few statements just to clarify. An arithmetic sequence is a type of sequence. An arithmetic series is a type of sequence. An arithmetic series is not an arithmetic sequence. Okay, all those statements are true. So if your understanding disagrees with any of those, maybe have a rewind or keep listening and we'll just try and clarify. So an arithmetic series is effectively defined from an arithmetic sequence, and this is what the official definition is. So an arithmetic series is a sequence created by summing the terms consecutively, in an arithmetic sequence. Okay. And of course, the sequence that you start with, the arithmetic sequence you start with, doesn't have to be 1, 2, 3, 4, 5. It can be any of the arithmetic sequences that we've talked about, 7, 10, 13, and so on. You add up the initial values up to a certain point, and that is your term in the arithmetic series. So we're now going to look at the general term of an arithmetic series. So it's a bit like that 1 to 100 problem, but now even more general. And to do that, we're going to first quickly write down what the general term for an arithmetic sequence is first. So if you remember, the first term in an arithmetic sequence was A. Right, by definition, we call the first term A. That's a sequence. The second term is A plus D, A plus 2D, and A plus 3D, and so on. I shouldn't say plus there, sorry, no pluses. Dot, dot, dot. And your nth term is A plus n minus 1D. Okay, and let's just write above here as well. This is for n equals 1, n equals 2, n equals 3. Actually, I think, no, that's confusing to say n equals there. That doesn't really make any sense. Instead, I'm just going to write first, second, third, fourth, and nth term. Okay, yeah, now that makes sense. So that's a general arithmetic sequence. All arithmetic sequences in the world can be described in this form. And now, from that, let's see what the arithmetic series looks like. Arithmetic series. So the first term is the same, right? Adding one number up is just that number itself. Then I'm going to add the first two numbers, right? A and A plus D, and I'll get 2A plus D. Then I'll add the first three numbers. So I'll have A plus D plus A plus 2D. That gives me 3A's and 3D's total. Then let's do the first four. We'll have 4A's and how many D's? 0, 1, 2, 3 for a total of 6 D's. Okay, dot, dot, dot. And then what? What is the nth term? Okay, we'll look at that in a moment. But this is what we're effectively asking here. This thing here was the general term, right? This was the general term for an arithmetic sequence. So the question now is, what is our general term here for an arithmetic series? Well, what we're going to do is we're going to use the Gauss 1 to 100 trick. Exactly the same trick, except instead of doing it on numbers 1 to 100, we're going to do it on numbers A plus D, A plus 2D, up to A plus n minus 1D. Okay? Because ultimately these things here are just numbers. We're going to add them up. We're going to add up all of these. I don't know how many there are. There's n of them. I don't know what that number n is, but we're going to add them up nonetheless. So let's do this carefully and have a think about how this works analogously. So with the 1 to 100 trick, we took the first term, 1, and we took the last term, 100, and added those two together. So let's do the same here. Let's create our first pairing. It's going to be A plus, so this A here, plus the last term, which is in this case A plus n minus 1 D. Okay? And now let's take our next pairing, our second pairing, which is the second term, in this case A plus D, and we're going to take our second last term, right? Which it's somewhere buried in these dot dot dots, right? But our second last, let's call it n minus 1, is a plus n minus 2d, right? That's the second last term. So if I put that here now and pair it up, right? Much like the 1 to 100 trick, you're going to find all of your pairings add up to the same expression, right? From 1 to 100, we had pairings which added up to 101. For this case, we've got pairings that are adding up to exactly the same expression every time. Here I've got a plus n minus 1d, right? Which is 2a plus n minus 1d. And here I've also got, in the second one, I've also got 2a, and I've got here a d and n minus 2d, so add that together, you get n minus 1d, right? So same thing again, right? This is all the 1 to 100 trick, just with a lot of letters involved instead. So we've got the same sum each time. So now I'm not even going to bother writing the next pairing because I think we've convinced ourselves this should work. All we need to know is how many times are we going to do this? How many pairings? So with the 1 to 100 trick, had 50 pairs, right? 100 divided by 2 is 50. In this case, we've got n terms, so how many pairings? N over 2, right? So this will be done in total, this adding up, we're going to do it n over 2 times, okay? So finally, all we do is we take this pair total, and we multiply it by n over 2, and we're going to get our full total of this whole sequence, this full arithmetic sequence, which will give us the thing we're looking for here, the general term. Okay, so let's just write it in. That general term here is going to be 2a plus n minus 1d, which was this, multiplied by n over 2. And that's it. That's our general term for a arithmetic series. Okay, so it looks a little bit complicated. I think it's in the formula book. Having said that, it is worth remembering. I'm just going to rub off some of the working here. And I also just want to give you a nice trick for remembering this. And the trick ultimately comes from how we derived it in the first place. Okay, a plus n minus 1d, I don't think it's too hard to remember. It's eventually saying take the first value and add on d n minus 1 times. Makes sense. This one, it's a bit less intuitive why it looks the way it does, but what I suggest you do is the following. The formula, the big formula of the day for this session is this. Okay, but I would recommend, rather than thinking of 2a, we're just going to think of it as a plus a. And then remember that this is our first term, right? This is u1, a. And this thing here, a plus n minus 1d, that's the nth term. That's this thing up here, right? So this is un, our nth term, right, where u is an arithmetic sequence. So really, the formula is a lot simpler than it might first appear. It's effectively saying divide n by 2, take the first term, take the first term, call it u1 or a, and add the last term, un, and that's it. Okay, so that's equivalent. These are exactly the same thing. Okay, where u is the arithmetic sequence that the arithmetic series is based on. Okay, hopefully that wasn't too complicated. Hopefully, at the very least, you were able to follow along. You won't have to prove what I've just proven here. You won't have to be you're not going to be expected to rederive all this, but you are going to be expected to use this formula here in purple, and also this one here. You won't be expected to memorize them, but I expect you to memorize them because I think you're going to be using them a lot. So please do remember them. As I've said, this version is easier to remember in any case. If you can remember this, you can remember this, and therefore you can rederive this thing in purple. Okay, so first example in the textbook. We don't need to do it, we just did it. Prove that the sum of the first n terms of an arithmetic series is that. I said you wouldn't be asked to do this. In an exam you wouldn't be. This example is given in the textbook precisely because they deem it, and I agree, you want to know how to do that. Because by understanding how it's derived, you have effectively understood the whole point of series and how they work. So that example, we basically just did it. Okay, so now let's start actually using the formula to answer interesting questions. So find the sum of the first 50 terms of the following arithmetic series. 32 plus 27 plus 22 plus 17 plus 12. Okay, I just want to define terms more than you'd normally need to just make things clear. Okay, because it said here this is an arithmetic series and then it's just added up a bunch of numbers. Personally, I find that a little bit confusing. It's a weird way of, because ultimately a series is also a sequence. So they haven't actually listed the series here. What they've done is they've listed the numbers that add up to make the series. So I want to just define this formally. The arithmetic sequence that underlies this series is the following. It's U1 is 32, it's U2 equals 27, it's U3 equals 22, U4 is 17, U5 is 12, and so on. The arithmetic series, sorry, I spelt it wrong up there. The arithmetic series, and we didn't use a notation yet actually, so I'm going to introduce it now. We tend to use S, capital S. So rather than talk about U1 and U2, we talk about S1 and S2, right? But they correspond to each other in some way. So S1 is the same. S2, this is 32 plus 27. Okay, and I'll just write it in, I won't work it out. S3 is 32 plus 27 plus 22. S4, the fourth term in the series, is 32 plus 27 plus 22 plus 17, and so on and so on. And Sn is the formula that we just talked about. It's n over 2, 2a plus n minus 1d. Right? Where in this case, a is this thing, 32, and d is, remember, the d corresponds to the original sequence, right? In this case, the d is minus 5. Okay, so what have we been asked to find? The first 50 terms. Okay, so that's what we're going to do. We're going to find S50 effectively, S50. So S50 is going to be 50 divided by 2 times 2 times A plus m minus 1, which is 49, times D, which is minus 5. Okay, so we work all that out, we get 25 times 64 minus 245. Something's gone wrong, hasn't it? When I get a negative number. Ah, no, that does make sense actually. Sorry, no, nothing's gone wrong. Except my intuition was wrong. So remember this arithmetic sequence, this sequence 32, 27, 22. Yeah, that is an arithmetic sequence. 32, 27, 22 is eventually going to start having negative terms. We just didn't see any of them yet. So this sequence is eventually going to start having -3, -8, and so on. So actually S50 is mostly going to be adding negative numbers, so it makes sense that S50 will end up being a negative answer at the end. So let me finish off that number there. That was 49 times minus 5 is minus 245. Gives us 25 times minus 81, minus 181, sorry, which gives us minus 4525. And that's the answer. That's the 50th term in the arithmetic series, is minus 4525. Okay? So the 50th term of the arithmetic series is the same thing as summing the first 50 terms of an arithmetic sequence. In fact, I might even argue that the way that that example has phrased it is a bit dodgy. To say summing the first 50 terms of the arithmetic series is I wouldn't phrase it that way. But based on the topic we're studying, it's clear what it actually meant. It effectively said, do 32 plus 27 plus 22 plus, and so on, so on, so on, with 50 numbers. Okay, so I think even the textbook can word it slightly weirdly. When in doubt, just ask me. So make sure we're clear on what a sequence is, what an arithmetic sequence is, and what an arithmetic series is. Okay, so now we're going to talk about, in this example, how certain sums of sequences, or in other words series, eventually hit certain numbers, and we want to know when that happens. So we're trying to find the value of n for which something happens. In this case, we've got a question saying, what's the least number of terms, so what's the first time, in this addition, 4 plus 9 plus 14 plus 19, that we eventually get to 2000. So how many numbers, right? So if you said to me, oh, the answer is n equals 4, then I would say, well, 4 plus 9 is 13, plus 14 is 27, plus 19 is 46. So you're wrong. It hasn't hit 2000 yet. So n must be bigger than 4. So the question is when, right? How many terms are we going to need for it to exceed 2000? So we're going to use the formula. We're going to find an expression for the sum of the arithmetic sequence, or the nth term of the series. The underlying sequence is 4, 9, 14, 19. That's our arithmetic sequence. It has an a of 4. It has a d of 5. The arithmetic series correspondingly has the nth term Sn, and that will be n over 2 times, and in this case I'm going to use the first term last term method, so it'll be n over 2 times u1 plus un, right? So let's practice using that. In that case, that's n over 2 times a plus a plus n minus 1d, which is our nth term of the sequence. That gives us n over 2, and now we plug in the values. 4 plus 4 is 8, plus n minus 1 times d, which is 5, and let's stick that after the plus sign. So we get this. Okay, so that's our nth term of the series. So now we're asking, when is that more than 2000? So now we can just ask this question like that. And now we turn the whole thing to just solving an inequality. So let's do it. So if I go up here, I'm going to multiply both sides by 2, and we'll get the following. It's greater than 4000. Now I'm going to multiply out the left-hand side to get a quadratic. So we've got 8n plus 5n squared minus 5n is greater than 4000. So that's 5n squared plus 3n minus 4000 is greater than 0. Now, you know how to solve inequalities, and hopefully you do remember how to solve an inequality where one side is the quadratic. Effectively, you're going to have two regions, right, where it's the case. I do think, though, it's probably easiest at this point to not worry too much about what the graph looks like or the regions, and just pretend it's an equals. Find the two values for n. One of them will be invalid because it will be negative, and the other will be the one you're interested in. Okay, so that's probably easier. That technique I'm advising when we're working with sequences and series. So pretend it's equals, solve the quadratic. We can just use the calculator if you're feeling a bit lazy. In this case, we end up with something like 28.0 and minus 28.6. Now we have to be careful. I'm just going by the textbook here, so we're going to disregard immediately the negative value, right? Because n definitely can't ever be negative. We start counting from 1. So it's the 28. And then you just have to be careful. Is it 27? Is it 28? Is it 29? It depends on how this was rounded. But in this case, assuming it is in fact a number more than 28, so 28.01 for instance, that means it hit 2000 at 28.01. So yeah, in that case you'd say 29 terms would be sufficient. So I think the actual value before it was rounded would have been something just under 28, maybe 27.99 or something like that. So yeah, round up, effectively. Round up, get your integer from the rounded up value. In this case, the answer is 28. Okay, so some questions for you to try. They're all on this slide. Much like before, where there was one key formula you want to use, in this session, your key formula is this one. Okay, that's the sum, or that's the nth term of a series, where a series is the sum of the first n terms of a sequence, arithmetic series. Or you can remember this version. They are exactly the same, they're equivalent. Okay. So make use of that formula. Remember about your A's and your D's in the underlying arithmetic sequence. Have a go at these 5 questions. There's some nice ones. Pause the video now.